Hello and welcome back. If you follow the channel, you already know that my HP 9825, famously used by Mr. Fancy Pants in the HP catalog, recently died from a power supply failure that caused an overvoltage. In the previous episode, we attempted to repair our faulty RAM. From the logic analyzer trace, we suspected a memory refresh problem. But we got stumped by the complicated TTL noodle logic that implements the DRAM controller. We clearly got very different results from our working 9825 that we use as a reference. Both machines showed the same tick signal that starts the refresh cycle on the yellow trace, but the response to the refresh seemed completely different. In particular, pay attention to the blue count signal, the one that advances the refresh counter. They look nothing like each other. One is mostly high with short low periods of various length, while the other is mostly low with very short, even length high pulses. We were pretty sure we'd soon find a big bad faulty gate in the noodle logic, but they all tested good, and the circuit is so devilishly interconnected with so many re-entrant loops that we could not determine what was a cause and what was an effect. That's when I decided to try to simulate it. I used the Logisim Evolution software, about which I just made an intro tutorial in my previous video. Here is the grand simulation of our RAM control noodle logic. It is even more noodly and circuitous than I anticipated, but it appears to work well in the simulation. But before we dive into it, we need to take a step back and explain what it is supposed to do in the grander scheme of things. Maestro, please give us the elevator music. So it's supposed to help us connect the processor to its memory, and as you remember from the previous episodes, the memory are 16K by 1 DRAM, so there's a whole bunch of them, and out come the bits, one per chip. You also remember that it's quite peculiar in its addressing. It has only 7 bits of input, so you input them in 2 chunks, one called the row, one called the column, at 7 bits each, and use the RAS and the CAS lines to tell it which it is. So in order to help you do that, there is a chip that we haven't talked about yet, but that's quite important. It's the Intel 3242 DRAM controller. It mostly consists of a 3-to-1 multiplexer. It has 3 ports of 7 bits each at the input. The first one is aptly called row, and it's for giving the row address to the RAM chip, obviously. If it were logical, you would connect it to lines A0, A6. In the 9825, actually, it's in complete disorder. They just pick 7 random bits from the address bus, but it really doesn't matter, I guess. Same, you have a column bus that's would be connected to A7 to A13, so that gives you your 14 bits of address, which you will multiplex one at a time into the row and the column of the RAM chip. It also helps you with the refresh. There is a third port of 7 bits that exposes a 7-bit counter, which you present at refresh time to the memory, and there is also a pin to increment the counter, so you can scan the whole memory. And basically what our RAM control noodle logic does is control those 2 chips and their inputs. It controls obviously the RAS and the CAS line at the same time as it controls the row. And then at some point it needs to do some refresh, so it will toggle the muxer to the refresh port, expose the counter, and do the count increment when it needs to. And it does that using some inputs from the processor. So what are those? There are not that many. The first one is ADDR. It comes out of the memory decoder, and the upper 32K bytes indicated by A14 would be the RAM, but they added some slivers of ROMs, the plug-in ROMs that go in the front of the machine, so they also need to look at A13 and A12 and subtract that from the addressable RAM space. Nevertheless, A14 is important. They pass it directly, and basically when A14 is at 0, you know for sure that you are in ROM. A15 is actually not used for addressing, it's used to indicate byte operations. We'll ignore it. And finally, STM is the start memory cycle. It's the most important timing signal, and we repaired it when we were doing the ROM repair. So that's it. Basically what our noodle logic has to do is generate those 5 outputs out of those 4 inputs plus the clock, and it's way more complicated than you'd think.
And now, before the next show starts, let's enjoy an intermission. You'll find our snack bar chock full of good things to eat and drink. Tasty, tempting hot dogs, thirst-quenching soft drinks, fresh, crunchy popcorn, a complete assortment of delicious candy, and a full line of cigarettes. You've plenty of time, so visit the snack bar now.
Alright, I hope you had time to hit the bar, because in the second part of this video we are going to deep dive into the noodle logic. So here's the grand refresh logic circuitry. You recognize my little generator in the top. So here's the clock, and then I generate STM using the technique I demonstrated in my Logisim video. So I have clock, STM, A14 and address as my input mostly. And you can see that some of the noodle logic simplified really well and some didn't. The one that simplified really well is the RAS and the CAS. So RAS is very simple. It takes STM, and when it's addressed, it outputs it. So actually, let me change that one here. Let me make it addressed, and we should have RAS. Here is RAS. And then if I address it to, we should get CAS, which is also very simple. It's basically a slightly modified STM, and when the row is switched in from the Intel chip, then there's a slight delay. And you see it coming here, so RAS follows STM, and the column comes just slightly after when the row has switched. So no problem here, that easy to debug and easy to understand. The one that didn't simplify at all was this here, which is the control for the 2 signals, the refresh, which is that little light here, and you find it over here somewhere, Intel refresh, that exposes the Intel refresh counter, and the flag, which is actually flag is the same as count. It updates the counter. So to do those two, you have this incredibly complicated logic, which is driven by a timer in the middle. So if you follow the clock here, it's directly driving this, which is a divide by 10. And you have another divide by 10, so it's a divide by 100, but already you can see that it's in a snake loop that eats itself. The output of the divide by 10 triggers the other divide by 10, but it comes back here, it's mixed together, and it's held here. And the whole point of that is to generate variable times for refresh that align correctly with the memory cycle when it's addressed. So anyhow, you will hear when the time comes up for a refresh, it will have the low beep. And there's one coming up soon, right here. Here we go. And so the low beep was the time to start the refresh, and the high beep is when the refresh actually happens. And depending on the timing of the memory, it can happen right after the counter has timed out, or it can take a while to align on the memory cycle, so the refresh doesn't trump on a current cycle by the processor. And this is all very complicated. These 2 gates control when the refresh counter is exposed, and it's also completely loopy. This one is armed by the time signal, but it has to wait for this one to come up, which waits for the STM, and then when it comes off, it has to wait for this one, which comes back here and comes back here. So no wonder we couldn't figure out what was coming out. Once again, this whole thing didn't work until I put the last wire. Same for the counter increment. it has its own set of flip-flops here that are all imbricated into each other, and they wait for some of this and for some of that. It's just a miracle that this works, actually. And then something I didn't quite understand either is that there are two different refresh mechanisms that leads to two complete different timings. There is a refresh when the memory is accessed. Right now, it's a RAM access, and it relies on all those flip-flops. But if I turn that off and I do a ROM access, so now the ROM is getting accessed and everything calms down. It's totally quiet, there's no RAM access. And then when the refresh finally happens, it's not going to use any of those gates. It's going to use these ones and do a totally different logic. Let's wait for it. Here you go. So you have a very short time, and you have this refresh, which is aligned completely differently. So when I realized that those were two completely independent and complicated refresh mechanisms, it started to make sense. So let's wait for the next refresh cycle on this one, and this is a refresh when we're accessing ROM. And let's look at what our counter does. So right now the counter is mostly up. The refresh is going to come up, and there you go. Here comes the refresh. And the counter goes down, and it's going to come back up after the refresh cycle has actually happened. So in this condition, the blue traces that we saw on the scope will be mostly up and sometimes down. Now let me change things and make a refresh during a RAM access. So let's wait for the next refresh cycle here. Okay, refresh coming up. Here it goes. Actually, I'll stop it. And now it's a completely different refresh cycle. It's triggered by the ref gate over here. And look at the count line. It's completely different. It's mostly low. And during the refresh, it does this very short up. And as soon as I discovered that, I had a revelation. This is what we were seeing. Since on the good machine and the bad machine, the processor is not executing the same instructions because one boots, one doesn't. One was stuck in ROM and was doing the refreshes one way, basically where we had the count mostly high and coming down from time to time. And the other one was stuck in memory somewhere and was doing this refresh where the count is low most of the time and goes up in very short bursts. All of a sudden I realized that, oh, maybe we were all frazzled by these machines reacting completely differently. And maybe the refresh logic works, it's just that one is stuck in one refresh mode and the other one is stuck in the other refresh mode because of the processor activity. So all of a sudden, I started to suspect a completely different part of the circuit. It's either something in the devilish logic here, or something could happen with our little memory controller. So a couple episodes ago, we already knew we had an either-or situation, and we only went after the refresh noodle logic, mostly because of the logic analyzer traces. But the simulation is now telling us that we should probably question our Intel controller instead. I have added a few pods to the configuration, so now pod 6 is testing the RAM and the 6 bits of address. And also it has a line on the Intel chip for the refresh signal. So the idea is to try to catch a refresh cycle and see if the address counts. So it's a very basic setup. So off we go, trying to capture refresh cycles. Okay, captured a few. Okay, eventually it starts. It was 40, 41, and then it went to 10,000 something. It's stuck in a RAM checking loop, but I see no refresh address. Nothing, still 0. Or it might be that my Intel chip is so zapped that it doesn't provide any address to the RAM. So I've now added the scope to the mix here, and so I have row selection, column selection, and 2 address bits. And see if that wiggles at all. I'm getting worried here that nothing's happening in the memory. I never saw any addresses. They're all at 0. And then you see the processor working for a while before it hangs. Let's do it again. Start up, boom, hung. And then this must be a refresh cycle. This on top of that. Okay, yeah. So refresh cycle happens when there is a row selection not followed by a column selection. There should be a row column. But if it's just row, this is not for the purpose of reading. There is no column, that's a refresh. So the refresh circuitry is commanding a refresh, but it's only taking care of one address. So this is probably what's happening. We have only 1 byte of memory or 1 word of memory in the whole thing that works. It's never translating the addresses. Addresses don't come to my RAM chip. So if my theory is right about the RAM controller just not feeding the correct address to the RAM, actually feeding only one address, 0, that would explain why the memory checks good, because we check only the position 0, right? No matter what address comes in the chip, what is given to the RAM is always 0, so that's always good. But I should be able to check if we are shoving everything into the same address. Then when I read the wrong return, where is it? It's over here. That number 010077, which I thought was random, should not be random. It should be what the last address to RAM was, and it's all shoved into 000. And so I just need to see what the last write was. So it would be, it's right here. It's here. It wrote, it works. It tried to write into address 77261. It tried to write 010077. And of course that went into address 0 because our decoding is not working. And that's exactly what we read back. And so it works on this trace. Let me look at the other trace, see if that confirms it. So that's the most recent trace I got. Oh, right there. Yeah, so same thing here. Before it accesses this, it tried to write 077134 to address 77353, and of course that went into address RAM 0. And then when it reads it back here, trying to read from 77634, it reads it back from 0 and retrieves exactly that. I think my theory is right. Refresh is working. It didn't lose it with refresh. It just gets all mangled up because we have only 1 word of address that's alive in our whole memory here. We can't access the rest. So I've taken the board off and I'm going to take the Intel chip out. So that must have been premonition. I put a sticker to distinguish our good board from our bad board, and I put bad right on the Intel chip. Alright, so a good early chip from Intel. As you guys might know, Intel is a company that's dear to my heart because I spent quite a bit of time there. I was actually an Intel fellow once. Here we go. And now if I put 1, 1, and I turn ref on, it doesn't come out. It's at 0. And if I turn refresh on, I up the count, and it's not counting up. So yeah, chip confirmed dead. And no, those 2 bits, when I do row, they should have come out here, and they didn't. And then when I do refresh and I count up, they should have come over here, and they didn't either. So we're pretty much hosed. The chip is completely dead. Looks like my new old Intel chip has arrived. Now it didn't say if it was working or not. It said used. This looks completely new in original deteriorating foam, so hopes are high. So I went ahead and built a little demonstrator for the Intel DRAM controller chip. So I now have 6 bits of input for the row address on these wheels, 6 bits of input for the column address, and I'm reading the multiplex output also on 6 bits. Those are simply BCD to 7 segment decoders and 3 bits each. So it's all in octal, by the way. So right now I am on row, and it should follow this set of wheels, and it does. So it's basically taking the inputs from over here, the 6 bits, and connecting them to the outputs. And if I switch it in a row, yeah, it says 13, so it went up to 13, right? It's controlled by these now. And then the next one is just refresh. I just do refresh. And right now the refresh counter is at 20, so if I want to refresh the next row, I give it a count. So it comes from the internal counter in the chip. So it's doing what it should. It just switches between refresh and the row and column inputs, and chooses one out of the 3 ports. Okay, now I have the chip that comes from the 1925 and that I think is bad. If we turn it on, shows 77. And it's in a row, so it should respond to this. No cigar, ignores it completely. Now if I switch to column, it's still 77, should respond to this one, it doesn't. If I put it to refresh, it's still 77, and no, doesn't count a bit. I don't know if this is our only problem in RAM, but this chip is no good. It's totally zapped.
It's easier.
Here we go. This time I'll check it under the binocular.
So it comes with 3 pieces. There's also a little logic.
I'm good to go. I put back the board with the new old chip, the new Intel chip. I have the logic analyzer set up to look at refresh directly at the RAM. So if I do run and turn it on, didn't do a thing. Stop. Huh. Well, am I doing anything completely wrong here? I could.
You got something grounded that's keeping the
Yeah.
reset or
Yeah, I know, I do. Right here, that's not right. So the RAM doesn't have the regular arrangement of TTL power supplies, and I put it wrong. So I shorted ground to -12. That might not be good. I'll try again. Run.
you got it.
Oh, it booted. There you go.
Yep, and it was filling memory a level.
Okay. All right. So, okay, we got it. So we have RAM. It booted. That was the user fault. Okay. So you should see, if I set that one up correctly, you should be able to scroll down and see refresh RAM address. Yeah, I see it. 1, 2, 3, 4, 5, 6. It's refreshing. You see it here?
Yeah.
Okay, so I see the refresh. It counts 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, G. So that's what we were missing. The Intel chip wasn't just sending the addresses, and now it sends the counter, goes to 3F, goes back down. So it seems to be back. If I do a simple print command, that did work. I do a display command. That did work too. If I do 2 plus 2, it works. So most of it works. We're still missing a ROM, so this has the string in it. So if I do a string operation, I suppose that's not going to work. Dim Okay, $14, and gives me an error. So we're back to a B missing one of the advanced ROMs, and all in all, it wasn't that bad. And they were 4 chips, actually 5 chips, because Ken took the Intel one. So 3 TTL, the Intel controller, and a ROM that went bad. And I suspect that ratio is to keep constant. We probably have about the same number of bad chips on the A25 board, which we would need to bring this back to a T level. Also on the processor board we had 0 chips failed, so we'll see where that goes, but it's encouraging. So this had been a long time coming. 1 board down, 3 more to go, but this is quite a major step. The 9025 is back alive finally. So see you in the next episode.